Testing, testing. So we're going to finish up the moments of inertia stuff. Yesterday we learned how to do the calculation of the moment of inertia integrals for the cross-sectional area of a beam. And this is the most important takeaway from all that. There's different ways of setting up the integral to do that. If you're using a horizontal strip or a vertical strip, you can use either one for Ix and Iy. And the formula is a little bit different, as we explained in yesterday's lecture. So this should be on everybody's cheat sheet for the final exam. These will be final exam questions. These aren't going to be on test 4. What we're going to look at today is the parallel axis theorem, which is how we, it's a necessary component of doing composite body analysis, just like we're able to do centroids of bodies that are made up of simple shapes. We can do moments of inertia of beams whose cross-sectional areas are composed of simple shapes as well. So that's the thing. The only thing we need to do is be able to shift things. That's part of the composite body issue. So oops, going the wrong way here. With the parallel axis theorem, the idea is what happens if you know the moment of inertia about, say, one of these axes, and you want to know it about the other. So, for instance, suppose you know what Ix prime is. In fact, this is kind of helpful when you look at the tables. A lot of times, well, you can see what they do. They kind of specify Ix prime and Ix, and for a lot of these things, right? Ix prime and Ix. They're specifying both of them for you to kind of save you the trouble. Here, they're just specifying Ix, and they're not specifying Ix prime. Here, also, they're only specifying Ix, but they're not telling you. You can look up the centroid somewhere else, but the question is, if you know Ix, how do you find Ix prime, right? This would be like the x prime axis, which is going through the centroid of the body. So there may be situations where you need to shift the formula that you get from the table to apply to a different axis through the body for some reason or other. So that's what we have to learn the parallel axis theorem for. And again, here they're showing, and these are described differently. Here they're showing, you know, I bar, which is the moment of inertia with respect to a tangent. Well, actually, I bar is the moment of inertia about the axis. And however, yeah, here they're giving us IA prime, and we want to know what it is about the centroidal axis B prime. So in all those cases, we're going to have to shift the axis, and by doing that, we're changing the relationship, that characteristic distance between the differential areas and the reference point that we're looking at, right? So because we define Ix as the integral of y squared times dA. And if we look at this diagram here, we actually have two axes on here. We can think about a particular dA appearing in this body that would be part of the integral, right? And that dA appears on the x prime axis at some value, we'll just call it x prime. And it appears on the x axis at some point x. And the centroid of the body is indicated, and the x prime, y prime axes are going through that. So this is the location of the centroid on the x-axis. Let's look at the origin on the x prime axis. And this is the centroid location on the y-axis. And then also, there's this, y prime value, which corresponds to this y value on the y-axis. And these are all kind of orthogonally aligned. Like so. And by observing this, you can see, well, what is y? If you're doing this y squared dA to find the moment of inertia about the x-axis, well, what is y? Well, y, you can think of y as y prime, which is this distance here, and y bar, which is this distance here. You could add those two together, and you'll basically just get y, right? So that integral can be rewritten as the integral of y prime plus y bar squared dA. Right, nothing really different there. We're just rephrasing how we're talking about y. And that is going to equal, if you take that and square it, it's going to equal y prime squared plus 2y prime y bar plus y bar squared dA. And that's a summation, so we can split that into separate integrals and say, all right, well, that means we've got the integral of y prime squared dA plus 2y bar, that is a constant, times the integral of y prime dA plus the integral of, y bar squared times the integral of the dA. So this is actually kind of convenient. You can see that the integral of y prime squared dA is what we're calling I bar x prime, the moment of inertia about the centroid axis. And it's the horizontal x prime axis, right? That's what we're calling I x prime bar.
Why is y bar a constant and y prime not?
Why is y bar a constant and y prime not? Because the center of gravity of the body, or the centroid of the body, is fixed.
Oh, it's the same
y bar. Yeah, and y bar is the distance between the x-axis and the centroid, horizontal centroid axis. Yeah. As the, y prime is the distance to the dA, which is changing across all that body, but the y bar value is fixed. So Ix prime bar is the first integral, and 2y bar, integral of y prime dA. Well, the integral of y prime dA is basically going to give us y bar a, but that's going to essentially, so this guy is basically giving us, oops, let me erase that a little bit. I didn't want to include the 2y bar. That is equal to essentially y bar prime a, right? That's that moment. That's the first moment in the y prime coordinate system, x prime y prime coordinate system. But what is a centroid in the y prime coordinate system? What is y prime bar?
I think I'm getting lost.
Yeah.
Like you got bars and primes.
Bars and primes and all that. We talked about x bar, y bar as the centroid. And if you just take away the x prime, y prime axes for a second, let's just think about this thing. And you've got a centroid here and x and y. And this distance y bar is the distance between the x-axis and the centroid, right? But what about if our x and y axes were right through the centroid? Well, we still have to have a way of referring to y bar. Y bar is the location of the centroid offset from the x-axis, right? So in this case, we're calling this x prime, y prime. And I want to know what is y bar in the x prime, y prime system? How far is the center of gravity from the x-axis, the x prime axis in the x prime, y prime system? Yeah, which is what we want to do, because then we can cancel out that term. So that basically equals 0 times a, which equals 0. So this term goes away. And then this integral here is just going to give us the area. So basically it's a translation of a coordinate system kind of thing, which you do a lot in linear algebra, right? And yeah. And so Ix is going to equal Ix prime bar, that's that first term. You happen to know what that is. Plus y bar squared a. Right, that's this term at the end here, y bar squared a. So in other words, if you want to, well, and by the way, the same thing applies for iy. You can do the same analysis. Say, well, and the iy is also going to be I y prime bar plus x bar squared a. Another thing you definitely got to have on your cheat sheet. Hey, you guys, could the conversation be a little softer? I'm afraid it's the whole audience is being distracted. My large audience can't focus right now. I'm concerned about that. So the purpose of this is to allow us to shift that axis, which can be very handy. So what are these things? Let's just describe these. So these guys are the moments in a non-centroidal XY system. Moments in a non-centroidal XY system. The X and Y axes are not, they're not aligned, or they're not going through the centroidal axes, right? They're not going through the centroid of that body. So they're just some random XY system, right? And what it's saying is the moments in those moments of inertia in those non-centroidal XY system is going to equal the, and what these guys are, these are the centroidal moments, the moments about the centroidal axis. We'll write that a little clearer, the centroidal. The centroidal moments, and x squared bar A. This is x bar is the centroid location in the xy coordinate system.
Are these the same as before when we had like Ix is the integral of y squared dA? Is this the same value or is this a different?
Is this the same value as the integral of y? Yeah, Ix is the integral of y squared dA.
Okay.
But it's just saying, suppose you know where the centroid is and you know what Ix is. You could find Ix prime using these two. So this can help you in a lot of different ways, and we're going to apply that on the next slide. Like if you know this guy, and you know the distance to the centroid and the area of the body, you can figure out what the moment of inertia is about the centroidal axis, right? Or if you know the moment of inertia about the centroidal axis and the area and the distance to another axis, you can figure out what Ix is about any axis that you want. So you don't have to do the integral all over again. And then this becomes a really nice shortcut when we do composite body analysis, because a lot of the parts of a body are going to have to be shifted. We may have the moment of motion of a rectangle, but if it's off the x-axis, you got to kind of apply some correction to that to get it to be the right number. And so that's what these formulas are going to do. So as an example, we'll run through how you would actually use these, right? So suppose we want to find the moment of inertia IT, of a circular area with respect to a tangent to the circle. Well, we're given the formula for the moment of inertia about the centroidal axis, and that's what the I bar tends to mean. If you see an I bar, that usually means it's about the centroid when you see this bar. Centroidal MI. And we can use that formula, which says basically, well, if you want to know what the moment of inertia is about the tangent to a circle, you can use that form, and you happen to know what the moment of inertia is about the centroid. Well, I tangent is going to equal I bar, which is the centroidal moment, plus y bar squared A, but y bar is basically R, right? It's the distance between the centroid and the tangent. So we can take that formula that we're given, 1/4 pi r to the 4th, and add to it r squared times the area, which is pi r squared. And so the answer is going to equal 5/4 pi r to the 4th. Right, so that's using that axis there. We're basically taking this number and shifting it so that it applies now to the moment about this axis. And this kind of goes into the whole thing about bending, all that stuff. Suppose you're, what I got to do some kind of demonstration, and but basically, it kind of makes sense to me that if you're bending something about this point here as opposed to about its center line, that's a different kind of stress on the object. You're pulling away more at this farther end than you are at this end. The distance is farther, so you have to kind of add. You get a larger moment arm, so you can add this, you know, pi r to the fourth value to that, which kind of accounts for the fact that now a lot of the material is farther away from the axis that you're computing this thing around.
So this would be just like if you were trying to build around the table.
Yeah, that's what I'm sort of thinking. But you know, how you determine where that, you know, axis is. You know, I guess if you're butting up against something, that would sort of make sense, right? To me, that makes sense. You know, this would be a good thing to do an experiment on. This would be a great lab to do. You know, because we could take some material and, but yeah, I don't know how you could actually make it, you know, I'd have to think about that. How you could make it, so I'll have to ask my colleagues how you could make it so that you force it to do the bending about an axis that's not about the centroid. It seems to me if you just take something and try to twist it, you're kind of doing it about the centroid already.
Yeah.
But if you can somehow, I don't know, yeah, that would be an interesting experiment. Because then maybe you can come up with some numbers. You know, we could do an analysis. This could actually be done probably in the materials class too. We could do this. We do some things like this in the materials class, but it's not to the same level of detail. But likewise, the moment of inertia of a triangle with respect to a centroidal axis. So now suppose you can find you can find the formula for a triangle about the x prime axis is 1/12 bh cubed. And but maybe you need it about the centroidal axis, right? So that parallel axis formula will allow you to compute that. So a prime, right, equals b prime, the centroidal moment, right, plus some y bar squared times a. So you can use that algebraically to find what ibb prime is. So ibb prime is going to equal a prime minus y bar squared a. So it's going to be smaller, right? The centroidal moment of inertia is always going to be smaller than any other moment of inertia, right? Moment of inertia about any other axis than the non-centroidal one. It's going to be bigger because the material, the centroidal one keeps the material as close as possible to the center line, right? The axis that you're doing it. The centroid sort of passes through that midpoint of the body. This is so abstract. It's a weird thing to throw in the last week of class when everything else we've been doing has been so, you know, commonsensical. Yeah. This is like the most bizarre thing. So it really needs some kind of a laboratory experience to kind of make it come. Maybe I could find something, throw something together for tomorrow. That'd be kind of fun. Probably not, but I'll think about it. So, so what that says is, well, we know that then that this equals, well, a prime we're given is 1/12 bh cubed. And y squared a, well, this distance here is the distance between, we know, the distance between the base of the triangle and the centroid is 1/3 of the height, right? So we have to subtract that. That's the distance to the centroid. That's our y bar, right? So we subtract out 1/3 h squared, and then the area, which is 1/2 times the base times the height. And that is going to equal, you can factor some things out of here, bh cubed times 1/12 minus 1/18, which is going to equal, that means that our goal, our ibb prime, equals 1/36 bh cubed.
So the ones with the bar,
Mm-hmm.
I B B prime bar is the moment of inertia about the B axis?
Yeah, the BB prime axis. IBB prime, I mean, you could just call it I bar.
Yeah.
It's sort of redundant because BB prime is the centroidal axis, and I bar means the moment of inertia about the centroidal axis, right? That's what, you know, when you see that bar across there, that's the centroidal moment of inertia. Yeah, and we're just shifting it. So we got to get up and do these things. We got to do, you'll see why and how you use this when we do this example here, right? So when you take a composite body, which is what we're trying to do, that's why we're doing this thing. You've got a strange body which can be broken up into a semicircle plus a rectangle minus a hole, right? And the total Ix is going to be I1x plus I2x plus minus I3x. However, you know, it wouldn't be appropriate to use the moment of inertia of a semicircle about its base for this composite body when the base is this distance away from the axis that you're maybe trying to do it about, right? If you're trying to find Ix, you've got to shift that. You know, you've got to add some stuff to that, right? Because that thing is not being bent about its base. It's being bent about an axis that's pretty far from its base. And that's why we have to use this parallel axis theorem formula because that makes this all work out numerically. Otherwise, the results aren't meaningful. So this process, we can take this object, which is a similar object I think that we've looked at before, and if we want to find Ix, we got to break it up into its pieces again. And the first part is a rectangle, and we're going to have this table that we're going to fill in just like we did for the centroid, right? Well, but now we're going to keep track of AI, the Y tilde, and the Ix prime. This is one way to do it, or Iix, which is the other way. So this is the centroidal one, right? This is centroidal. And this is relative to the x-axis. And we may not fill all of these in, but we need to get the Ix's filled in for each body. If we don't need the centroidal one, we won't calculate it. So a rectangle about its base. Well, the area is 3 squared, which is 9. And we know the formula because we did the formula for a rectangle about its base. Ix is going to be 1/3 times BH cubed, right? A rectangle about its base. So that's going to be 1/3 times 3 times 3 cubed. Which is 27 feet to the 4th power. So we tabulate all this stuff, and we find that AI is 9. What is Y tilde I? Y tilde I. Yeah, the distance to the centroid. It really should be a Y bar I, right? Yeah, it's the distance to the centroid right here, which is 1.5 feet. And so we put a 1.5 there. And Ix, which is 27. The rectangle. That one's pretty easy. Okay, next we're going to look at the triangle, and the triangle has an area A2, which is 1/2 times the base times the height, which is 4.5 feet squared. And therefore, we know from this previous example here with this triangle, we're just given this formula here, the centroid of a triangle about its base is, not centroid, the moment of inertia of a triangle about its base is 1/12 BH cubed. So you'll be referring to those tables a lot, right? So I2x is 1/12 BH cubed, which is 1/12 times 3 times 3 cubed, which is 6.75. Again, we don't need the centroidal one, but sometimes it'll be a nice intermediate step. We put all this information in row 2 of the table. The distance to the centroid, by the way, is 1 foot because it's a triangle and you got to go 1/3 of the way up from the base to get to the centroid, right? Okay, questions? So onwards, now we've got this semicircle that's tilted sideways. Okay, that's a little bit weird. And we'll have to, use those tables again, but A3 is 1/2 of pi r squared. So that's 1/2 pi times, well, the radius of this thing, which is 1.5, and the distance of the centroid is 1.5. So that's 1.5 squared. And that amounts to 3.53. So this is where we have to be, let's see. With a semicircle, we probably aren't going to find the moment of inertia of a semicircle about a tangent to the edge, one side, right? That's a little bit asking for a lot, right? When you look at the table here, the typical table shows you a semicircle, but it's showing you the moment of inertia about the centroidal axis of that circle, semicircle, right? And we would need to, shift that a certain distance. But if we find it about the centroidal axis, that is, for our purposes, that's fine. It's actually telling us here that Ix and Iy is the same, which is kind of interesting. When you look at this, this table thing, right? What it's saying is the moment of inertia about the x-axis, which is over here, is the same as the moment of inertia about the y-axis, which is right here. Even though the geometry is different when you're doing the integral, right? You've got the moment of inertia about the x-axis. You can think of all these rectangles going, this. But it's the same as if you did those, distance squared plus all those things that way, right? So it works out to be coincidentally the same value. That's usually for an odd-shaped body like that. That's kind of unusual. So we can take note of that and say, all right, if this semicircle is oriented this way, with an Iy of 1/8 pi r to the 4th, well, that Iy happens to be like the x prime axis. It's the moment of inertia about the x prime axis, the way it's tilted on our shape, right? You see that? So what we're calling the y-axis here is equivalent to the x prime axis of our circle. Just geometrically, that kind of makes sense, right? And I bar 3, x prime, so that is essentially the moment of inertia about that x prime axis of the third body is 1/8 pi r to the 4th, which is 1/8 pi times 1.5 to the 4th power, which equals 1.99. Debbie? Yeah, how are these similar, right? So what you have to do is you got to visualize this. You take this circle and you rotate it so it looks like this. And what we called the y-axis here is now going through the middle of that circle, which over on this diagram is what we're calling the x prime axis. Okay, and the parallel axis theorem, which you missed, Savneet, unfortunately, but I can go over it after the lecture real fast. I3x equals, what that's, the parallel axis theorem says, if you know the moment of inertia about the centroidal axis and you want to find it about another axis, you just have to take that centroidal moment of inertia and add to it the distance that you have to translate to go from one axis to the other. The separation distance between the x-axis and the x prime axis is 1.5 feet. So we take that, which is going to be the distance to the, we call this also, this distance is also called y bar. It's the height of the centroid from our x-axis. And the parallel axis theorem says, yeah, you just take that and you add to the 1.99, which is the moment of inertia centroid, about the centroidal axis, and you add to it 1.5 squared. That's the distance between x prime and x, which is y bar, times 3.53, which is the area of that body. And what you end up getting is 9.93 feet 4th power. I don't know why this thing is here, but just ignore that. So we can put all these things on our table: 3.53, 1.5, our ix prime. In this case, we sort of needed to calculate it as an intermediate step to finding ix. This, unfortunately, is a very, you got to like really focus on this to get these things. It's a really tedious sort of set of steps. This is where you just got to relax and just go through it and check your work 3 times every time you do a step. And then the last thing is you got to do this hole. Well, this hole has a radius of 1. And the height of that hole is the distance y bar, right? So this distance here is y bar sub 4. This here is the x prime axis going through the centroid. And that's still 1.5 feet because it's centered on the same center as the other circle, semicircle. Our area is negative, because it's a hole, pi r squared, not to the 4th. I'm getting used to writing r to the 4th here. And since r is 1, that's just minus pi times 1 squared, or just minus pi. And the moment of inertia of a circle about its centroidal axis is, according to the table, here's the circle, and these bars, Ix bar, Iy bar, are about the centroidal axes as 1/4 pi r to the 4th. And we have to subtract this because this is the absence of a piece. So this is the moment of inertia that whatever material that would have been there is not providing, which we accounted for in these other two shapes, the rectangle and the semicircle. We've counted for that material. Now we've got to remove it. So it has to be a negative contribution. And it's minus 1/4 pi r to the 4th, where in this case, r is 1, because that's the size of the hole. So minus 1/4 times pi times 1 to the 4th power, and that equals minus 0.785. And I for x, which equals, according to the parallel axis theorem, I for x prime plus y for squared bar a4 is going to help us translate that moment of inertia, which is about the x prime axis, to the x-axis, so we can add all those parts together, right? All those parts have to have a common reference so that when we add them together, you know, they make sense, right? So we've got to find the moment of inertia of each part about the x-axis. And that's probably why we're doing these initial calculations. It's not that you can sort of bend this thing about any arbitrary axis. It's just that when you have a multi-conglomerate piece, you got to have a common reference point to do the moment of inertia summation of all those parts, and then you can find it about a centroid if you need to. So the area is just tabulating all this stuff. The area is minus pi, because the distance to the centroid is 1.5 still from the x-axis. I for x prime is minus 0.785, and then the total about the x-axis is minus 7.85. And the negative gets even more negative because A4 is negative. This is always going to be positive, but that gives us a bigger negative number, which is a more larger contribution because of the distance to the x-axis. It's a larger negative contribution. The absence of that hole is significant more because that hole is not sitting on the x-axis. It's moved away from the x-axis. We have to increase the significance of that missing material. So that allows us to sum them all up, and Ix is the sum of all the Ix's. So we can add those things up. And this should equal 35.83. Just adding all these things together. Does that seem right? 27 plus 6 plus 9 minus 7. Yeah, so that equals 35.83 feet to the 4th power. So that is the total Ix of that part. But really, most often, I think what we're interested in when we're doing these calculations is what is the moment of inertia about that body's own neutral axis. Okay, and we did this calculation before when we did the centroid, and we found that the x prime axis, the centroidal axis of that body is 1.34 feet away from the x-axis. We did this calculation from the centroid lecture. So if we need to find the moment of inertia about the neutral axis of this body, we have to use the parallel axis theorem yet again. So Ix equals Ix prime bar plus Y bar squared A. And we can then solve for Ix prime bar as Ix minus Y bar squared A, or that's going to be 35.83 minus 1.34 squared times 13.89, which is the area of that body. That's the sum of all these area segments. And what we end up getting is the Ix prime bar is going to equal 10.89 feet to the fourth. And that's our final answer.
So that's the moment of inertia, the entire body about its centroid.
It's the moment of inertia of the entire body about its own centroidal axis, which is, I think, the more meaningful quantity that we're often wanting to get when you're trying to analyze a beam and stuff, right?
And this is like a cross section.
It's a cross section of a chunk of beam of some, why you'd have a beam like that, don't ask, you just do. But this thing is extending out. And it has a hole in it, maybe to run a cable through it or something. Anyway, it's just an exercise to do this calculation. And that's the last thing we have to be able to do, and we're going to do that tomorrow. Got one day to do it all. And I'll be giving out practice test 4 tomorrow. And we'll look at that on Monday. Test is on Tuesday, yeah. We have a review on Monday, where you can also bring in any moments of inertia questions you have. Sure, you'll have some.
For exam is only on
Friction and internal forces. Yeah. So that is the end of the last lecture of the semester for this class. Sorry? Yeah. That's okay, it's recorded, so.
Yeah, I guess.
Was there a test today? People are still taking it probably. People have to decompress after those things. Yeah. Stressful class.
This was about
So Savni, what you missed is the derivation of the parallel axis theorem, which you can pick up on video if you want, but basically, if you've got a centroidal axis and you have an arbitrary, the centroidal axis is the x prime, y prime, so these things are going right through the centroid body, and some arbitrary xy axis of a body, and you have some little dA. This is showing you a little dA here, showing you the distances in each of these axis systems. You're talking about translating the axis from one set to another. And the centroidal, the moment inertia calculation is the integral of y squared dA, meaning it's this distance. But this is the centroidal calculation about the x-axis. It's this distance here, which is y, and we got to square that times dA. We got to sum all those things up in the integral. That's what the integral is doing for us. But but now that you have this y prime x prime axis on here, you can say, well, wait a second, this y is really the sum of this distance here, which is y bar. This is the distance to the centroid from the y-axis, plus some value here, which you could call y prime, the distance from the x prime axis to the central, to that differential area. And if you break it up that way, you can express that, you square that term into these three terms. This thing here is the moment of inertia, because you're doing the integral of all the y prime squares, you're finding essentially the moment of inertia about the x prime axis. That's I bar x prime. The last term is going to give you y bar squared dA. That's just y bar, which is a constant because the centroid doesn't change and the xy axis is fixed. So this y bar isn't going to change. So y bar is a constant squared times dA. That's just going to give us the area. So that's just y bar squared times the area. That gives us this term here. And the middle term cancels out. It's a little bit tricky to see that, but what we're talking about with the middle term is integrating y prime dA, and with the y primes, some of the dAs have positive y primes. Another dA down here would have a negative y prime, and the way the centroid is defined to bisect the positive and negative evenly. There is no net, or you can think of it, if the x prime axis is going through the centroid of the body, the distance between the x prime axis and the centroid of the body is 0 because it's going right through it. So we can put a 0 for y prime bar, which is what this thing is. And that means this whole thing goes to 0. So that gives us these two terms, this one and this one, which is the parallel axis theorem, which says if you know the moment in a non-centroidal xy system, it's the sum of the centroid the moment of inertia about the centroid of the body, plus some shift based on how far you're moving it. This is sort of a delta y, how far you're shifting the axis from one to the other. This is a delta x. And the way we use these is to, if you know the moment of inertia of a circle about its centroid, typically defined with a bar over it, the moment of inertia about this centroid, but you need to know what it is about some other point, you can use this formula and take that centroidal moment of inertia and add to it the distance that you're translating, y bar squared times a, the area of the circle. So that tells you that it's going to be bigger if you're looking at an axis that's not about the centroid. I did this much more slowly in lecture if you want to watch it again, the beginning part, in case you want to get more clarity on it. But we'll do some problems tomorrow, and that should hopefully clarify things for you all.